morning. Hello, good morning. Time to start. Welcome back. I see that I didn't scare you off yesterday. There's still time. So today we're going to kind of, for all of those maybe who weren't here yesterday, wrap up a bit of the revision type stuff, although we're going to place the ideas that we revise in maybe a more sort of linear algebra abstract setting, and today we're actually going to lean into that a little bit harder as we retrack over some concepts that you've seen before. So just a quick reminder of what we covered yesterday, because I had to remind myself. We started with partial differentiation. I got a good question, by the way. What's this number? This number is the chapter in Calculus 3, which aligns with the text that I'm showing you. Now, if you go through the textbook, you'll find that it doesn't quite take the same theoretical perspective. The textbook is there to give you a lot more concrete examples, but your first source of truth should really be the lectures. Okay, so I reminded everyone how partial differentiation works, which is pretending everything is not a variable except the variable you care about, and then doing single variable calculus. That was your second year course. Done. Okay, then we proved quite a long elaborate proof, but basically showing that as long as we have certain conditions, we can switch the orders of derivatives. This is going to underpin, we're always going to assume that we have enough well-behavedness that we can do this. Putting this in the integral setting, this is called Fabini's theorem. You'll meet it properly in analysis, where you'll learn the really tight conditions that are required for this to hold. This doesn't just let us swap the orders of derivatives. Later on, it's going to let us swap the order of integrals as well. We're not going to explicitly call on it every time, but every time we do that, you can just remember that this is here. And one little slightly worrying thing we learned when we did this is even things like the mean value theorem have some additional complexity when we start to put it in these multivariable settings. And even though it didn't come about here, the sort of take-home is like, don't completely take for granted that everything you know works in other settings will necessarily photocopy into a vector calculus setting. But that's fine. We proved it. We're very clever. And then we moved on to tangent planes, which is really where the calculations start. Tangent planes are kind of the key ingredient of calculus, because calculus is, if nothing else, the study of the dynamics of your manifold on a tangent plane. That's why linearization and local linear spaces are so very important. And we came up with a definition of the best local approximation where we did this, but we're actually going to take another look at this definition today and try and come up with something that really depends intrinsically on the surface, and I'll explain what that means later, because we aren't quite there yet. Then we calculated a tangent plane, because somehow at the end of this I'm going to ask you to calculate stuff, so probably I should every now and then show you how to calculate stuff. Good job, you all calculated it. Okay, so let's move on to making sure everyone remembers everything. The chain rule. So the chain rule, like 90% of calculus proofs are just applying the chain rule about 10 times in a row. The chain rule is very, very important, and we're going to remind ourselves of what it means. Suppose we have some f of x, y. A lot of the statements we're going to make in class depend on two variables, but we'll generalize them to n variables down the track as and when we need them. Also, we're going to say x and y depend on some variable t. How does f change along its path? So what I mean by that is we have some f of x, y, which I've drawn there, and we're going to say, you know, this is x, this is y, this is x. So we have some curve in x and y. So this curve is x of t, y of t. And the question is, if I then look at how that curve goes on my graph, which might look something like this, what I have here is f of x of t, y of t. So this is a really helpful way that we're going to be thinking about these surfaces and the like all the way through. And of course, what you learned, and we aren't going to rederive this, you learned this in first year, is that there is a chain rule. And that chain rule says that if I want to know how f varies with t, then I take the partial derivative of f with respect to x and look at dx dt plus the partial derivative of f with respect to y, full derivative dy dt. So this is the chain rule. It's incredibly powerful. It's more powerful than it seems. We call this the total derivative to separate it from partial derivatives. But a thing we might like to do is say, what does this look like? Is there a way to simplify this? Well, there is. We're going to write this in vector form. So it is partial f partial x, partial f partial y, multiplied by dx dt, dy dt. Or if you like, it's the dot product of those two vectors, linear algebra. This is actually going to be much easier for us to generalize into a setting that is going to be incredibly important for the rest of the semester. So hopefully this is revision, but let's do a couple of examples and just see some fun applications. And the first thing we're going to do is derive the quotient rule. You all remember it. You probably learned it for the HSC, or I don't know, grade 7. I don't know when stuff is taught in New South Wales. H of fg. So we're going to define some function h, and all it sees is f and g. And that function is f over g. And just to make life easier, I will try and do all of these assumptions, but if I miss the odd, assume the denominator isn't 0. Just let me know. Or don't. You know what it's not. It can't be. And let f and g be functions of x. Okay, you probably derived this directly from the chain rule and the product rule as an exercise at some point in your life, but the chain rule makes it almost a direct photocopy. So just putting it up from before. You take a crack, actually. Take a minute. Warm yourselves up. Get your brains moving. I will write the chain rule up for anyone who's forgotten it in the era since the previous slide. So it's been suggested that I can keep the previous slide on this one and the new slide on this one. Is there anyone who couldn't see properly if I did that? Because if some of you can't see, then that's a problem. Okay, well, let's give that a try. I'll fish around and try and make that work while you do this problem. No, but I need to make sure I know which one's recording before I do that. Okay, I'll start that in the next hour, hopefully. There's only one of the two screens records, I believe. They should both record? Oh, brilliant. All right. So if I freeze toggle this one, nope. Nope. It says one is frozen, but I think we can agree that it is. Okay, that's not the one I want frozen, but there we go. Okay, now we're cooking with gas. All right. I 100% am going to forget to unfreeze 100 times over the course of the next hour, so if I do that, just let me know. Yell, you can interrupt me, I don't care. All right. Cool. This is way better. If you can't see, move, because I like this. All right, you've had enough time. Let's fill this out. Partial h, partial f is 1 over g. Derivative of df dx is arbitrary, so we'll leave that as it is for now. Minus partial f, partial h, partial g, which is f over g squared, g dx. If you can't remember that, go and revise your single variable calculus. We put that all over a common denominator, and we get g f dashed minus f g dashed over g squared. Try the product rule yourself. It's even easier. Okay, good. All right. Unfreeze, swipe, freeze. All right. Let's try something a bit more tricky, because I think many of you have probably tackled that one before. Let's look at a problem that's actually going to show us something interesting. So in this subject, I will rarely do an example just to waste time. Often the examples will highlight something that I want to draw out in the next section, and this is a very good example of that. So some students kind of mentally check out during examples, and you can, like, you'll still follow all the theory, but I don't recommend that, because the examples will show something that I want to talk a bit more about. So you've done this before. You did Math 1962 or 1062, and you're like, yeah, Chris, I get it, chain rule. You've done these before. Let's look at a slightly more complicated parametrization. So we're looking at this curve we drew the other day, z equals x squared minus y squared. And I'm going to say let x equal sine t and y equal cosine of t, which hopefully you will recognize is the parameterization of a circle. So we start at t equals 0. We start at t equals 0, where x is 1 because of cos t. Yep, those are backwards. We start at y equals 1 and x equals 0. So t equals 0. And then, as t increases, we go around our circle. Yep, good. So we go around our circle and we come back at t equals 2 pi. What that means for our graph is that in the xy plane, we are going x equals sine of t and y equals cosine of t, and we're interested in what the path that follows this does, which might do something like this, and then dip back over, and then come up like that. So we're looking at a path in x and y that follows this circle. Oh, that looks so much better on my screen. I'm going to draw that better. Oh, no, just do that. Yeah, solved. And on our surface, we're dipping down, we're going over the Pringle, we're coming up the other side, and we're going around like that. And of course, you know, we're going from 0 to 2 pi, but we could keep doing that dance forever. So we want to use the result we derived yesterday, or stated at least, to determine the tangent plane. But let's ask, what is the path on the surface? This is going to be very important. So this path here is our path on the graph. And that path that we're going to follow has 3 coordinates, the x, the y, and the z. The x is sine of t naught, is sine of t. The y is cosine of t. And the z is, well, do a bit of that. Sine squared minus cos squared is 1 minus 2 cos squared of t. A little bit of trigonometry there, but should be fine. Okay, so we have our path on the graph, and we want to see how the tangent plane changes as we move around this curve. So when we're here, the tangent plane is facing you, but as we move around the curve, the tangent plane evolves, and it's until eventually it's flat and then facing the other side. So the way a tangent path evolves along a curve is going to be quite important. So z is equal to, at some t naught, z of t naught is equal to, for the tangent plane, f of x naught, sorry, at z of t naught, but we won't include this just to save space. We know it's z. If we're on the tangent plane, z is that plus the linear contribution in the x direction times by however far we've moved in x, plus the linear contribution in the y direction times by how far we've moved in y. So this is a plane that is glued to our surface at a point and is tangent to our surface in every direction at that point. Okay, so we do our derivatives, and what we get is 1 minus 2 cos squared t naught, which comes from this, plus 2 y cos of t naught x minus sine of t naught. So everywhere I've written x naught, I've replaced it with sine of t naught. So everywhere I've written an x naught, I've replaced it with sine of t naught. Minus, sorry, there shouldn't be a y there. I don't know why I wrote that. Because I'm writing the wrong line. Good. Better. 2 sine t naught. Sorry, I apologize for the confusion. My notes are too small. I will fix that next time. Cos of t naught, y minus cos of t naught. And again, the same thing. Everywhere that I see y of t naught, I've replaced it with cos of t naught. So this was 2x, x minus x naught, which is the partial derivative of this with respect to x. Yeah, quite possibly. No, because this is, remember, this is x squared, so the partial derivative is 2x, which is 2 sine t. So the partial derivative with respect to y is minus 2y, so minus 2 cos. Good question, and that was one of the reasons I was second-guessing myself halfway through that. So good instinct. So that gives us our tangent plane. And as we pick different t naughts, so different positions along this curve, then we pick different locations on the graph, and this tells us the tangent plane for our graph. Okay, we also know how to calculate the normal vector, which was minus fx minus fy1. And I really mean a normal vector, because obviously the normal vector is not unique. It's more a basis of the normal space, if you like, but that is fine. A normal vector is given by minus 2 sine t naught, 2 cos t naught, and 1. Now, we can also calculate not just the tangent plane to the surface along that, but the tangent line to my curve at any point. So I can calculate the tangent line to gamma, and that is hopefully simple, and you remember is just the derivative with respect to gamma. That's the definition of what gamma gives us. So the tangent line is gamma dashed of t naught. So this is the derivative of these. So now we're cooking. So the tangent line is cos of t naught minus sine of t naught, and then the derivative of that thing, when you do a tiny bit of algebra, is 4 sine t naught cos t naught. Okay. Does anyone spot something really important? Tell your neighbor something really important about these two lines. Talk, tell your neighbor, don't tell me, I already know. Okay, hands up if your neighbor said something clever that you think is right. You know what? That's good enough. What did your neighbor tell you? Exactly right. These things are orthogonal, which is what we expected to see. So if we calculate this out, we get the tangent direction dotted with the normal direction at t naught is equal to 0. Good. Okay. So this actually suggests something a bit more fundamental and something that we're going to make use of, which is how we are really going to think about these tangent planes. Because we kind of constructed these tangent planes. We said, yeah, it's a local best linear approximation. And it is. But there are a lot of contexts where we might want to apply these ideas in settings where we can't even really look at what we're studying. You know, we are about to take these calculus ideas and abstract them to start talking about the calculus of vectors. And one of the tricky things that we're going to experience is that you can't always sort of see a tangent plane. You need a definition that you can trust. So in general, we have found that normal vectors can be constructed as minus fx minus fy1, at least in 2D. The construction of the normal vector is a little more complicated sometimes. And we can construct the tangent space by looking at the derivative of a curve in some way. So at the point t, a curve changes x dash t, y dash t, z dash of t. But we derived the chain rule precisely for this purpose, because the chain rule actually fixes this as being fx times by x dashed of t plus fy times by y dashed of t. And by direct computation between those two things, let's just remind ourselves that we use the chain rule here. By direct computation, just looking at those two quantities, we can see that gamma dashed of t dotted with n is equal to 0. Minus fx times x dashed minus fy times y dashed plus fx x dashed plus fy y dashed equals 0. The normal is always orthogonal to any tangent vector you might construct. Because I've said nothing about gamma in this. I've just said gamma is a curve that passes through the point, which means that any possible curve that passes through the point, this must be true. And that is actually how we're going to think about constructing tangent planes. So if we have some gamma, which follows x of t, y of t, and then it has a graph f of x t, y of t, left myself way too much space there. There we go. Is a curve on the graph f of x, y equals z, then gamma of t naught lies in the tangent plane to the graph of f of x, y. Okay, so the point on the curve at t naught lies in the tangent plane, and the second half, because that just tells us where the tangent plane is embedded, and gamma dash of t naught dotted with n is equal to 0. That is the definition of our tangent plane. And the proof is this. So this is what's called the intrinsic way to define a tangent plane. We don't have to say anything about the space in which our surface is embedded. We are defining it purely by things that happen on the plane, on the surface itself. So I'm saying I've got some point here on my surface, and it has some normal vector, which is defined as normal vectors are by properties of the surface. And I say, okay, well, I've got some curve. I've got some curve gamma 1 that passes through. Well, at this point, the tangent is this arrow here. So that vector is part of my tangent plane. Okay, if I come at it from a different direction, maybe I have a curve that goes like that, which I'll call gamma 2. So I've got a different curve now. I've completely forgot to untoggle, and none of you told me. So I have this curve. And now, I'll do it in a moment, got to finish my train of thought. If I start to put together all of these curves, all of these vectors, then I will get a vector space, and that vector space will be the tangent plane. And I've defined it purely by things that are going on in my surface. Yes? Yes. Yes, it is. Good. All right, let's untoggle, because as good as that is, there's no way I'm going to remember that for the 400-odd slides we're doing over the course of this semester. So as much as I would like that to work, I can only remember so many things at once, and most of those are vector calculus. So, look, you don't need this definition for a lot of the things that you're going to do. Writing down your local linear approximation is normally plenty, but as you get into sort of higher mathematics and more abstract spaces, if, for instance, you wanted to take differential geometry in third year, this is how you would be thinking of tangent planes. And this generalizes to concepts that you may have heard of, like tangent bundles and tangent flows and that sort of thing. So it's always good to have this kind of definition in your back pocket. If we put all of these arrows together, then we get a plane. And that plane is our tangent plane at the point. So the downside of this is obviously you need a set of an infinite number of curves, which is a pain to calculate. Okay, so let's put this together as a formal definition, because we do like advanced math here. And we're going to say, let G be the graph of a differentiable function. Then the tangent plane to the graph G at point P is denoted as the tangent plane at point P of G. And it is the set of vectors such that V is equal to gamma dashed of naught for gamma of t in G. Now, this is the guts of it, but there are a couple little technical points. Our curve doesn't have to be on G everywhere. It just has to be on G in some open region around 0. So t just has to live between minus epsilon and epsilon. So an open set of any size containing 0. And of course, gamma of naught has to be p. So this says that it passes through the point we care about, and it sticks around the point for long enough for the derivative to be calculated. That is, to my mind, a little more general than you need. You can restrict this in almost every setting you might care about to curves that just live on G, but we like to make our definitions as flexible as possible. So if you think of this as curves that live on G, you will never be wrong. Which means that I can write down all of my curves. I can say, well, here is my gamma 1, here is my gamma 2, here is my gamma 3, and I take all of their tangent vectors and I put them all together, and I get my tangent plane. Set of all possible tangent vectors. Nothing can escape. This should have the same dimension as G. If they don't have the same dimension as G, something funny is going on and you need to reevaluate your understanding of the surface. Should have the same dimension as G. Every possible tangent line at P lies in the tangent plane. Why is this useful? Because coming up with these local linear approximations and using those forms is very easy if we can write down our local linear approximation in a sensible way. But as we do more complicated structures, that becomes very hard to do. So we're going to do an example, and then I'm going to think we might take a break soon. And the example is a bit different. We're going to talk about the 3-sphere. So the 3-sphere is a sphere embedded in 4 dimensions. So the surface of the sphere itself is 3-dimensional. I'm quite good at this, and I can't really imagine that very well. You don't so much imagine higher geometry as get used to it. R4 is a particularly meddlesome geometry for reasons that are way outside the scope of this course. But, you know, so when I was first learning this, the professor who taught me some of this stuff was like, okay, the way to visualize Rn is to visualize R3 and then to close your eyes and say N. Like, there is just... I wish I could give you good intuition, but we are about to move into the sort of area where intuition doesn't always help, where geometry is useful, but if you try and rely too much on visualizing everything, it can be a bit of a crutch. So follow what you can visualize. Follow the geometry, but trust the algebra and trust the definitions, and you'll be in pretty good shape. This will all go out the window in weeks 5 and 6, where we're just going to pretend the whole world is three-dimensional and not think about anything else. But that will come later. For now, we trust algebra. So I have a three-sphere. If W is greater than 0, so we're going to find the tangent plane at a particular point, and I'm going to say it's a point where W is greater than 0. We'll talk about what it is in a moment. So this can be written as a graph where, because we have this relationship, sorry, wrong line. We have this graph, so it is x and y and z, and because W is positive, W is the square root of 1 minus x squared minus y squared minus z squared. So that is our surface. It's three-dimensional. It is in some sense of volume. And what we want to know is, all right, if I let P be the point 0, 0, 0, 1, what is the tangent plane of S cubed at that point? If I look at S2, S2 is the sphere, you know it, you love it, you've thrown it at people, then we can look at the tangent plane equivalently, which is, if I say W is the vertical direction, is this point here. And if I think about all the paths that can pass through this point, you know, you might get gamma 1, you might get gamma 2. You've got all of these paths passing through the point. The tangent plane at the very top of the sphere is a horizontal plane. Okay, you can kind of visualize that, and our definition of the local linear approximation would tell us exactly that. It's a little less clear what that means in this situation, because it's going to be, remember, our surface is 3D, so the tangent plane has to be 3D. So in some sense, it's going to be a three-dimensional space glued to our four-dimensional sphere. But that is the tangent plane, so we can just follow the definitions. What is TP of S cubed? So if we let M of t be A of t, B of t, C of t, D of t. Nope, again, that comes later. Yeah, we're doing this with matrices next. Let gamma of t be x of t, y of t, z of t, and w of t. So we have curves in space. And we want gamma of naught to be 0, 0, 0, 1. So our curves in space pass through the point we care about on our three-sphere. Okay? Well, we can calculate the derivative at that point of any arbitrary curve with the restriction that it passes through the point. The derivative, and if the derivative exists, then we're golden, is x dashed of naught, y dashed of naught, z dashed of naught, and w dashed of naught. And probably you're like, oh, that's right, he taught us the chain rule. Because w depends on t, but also on, well, w depends on x, y, and z, and x, y, and z depend on our variable t. So our first three are going to just be straight up derivatives, but the fourth one we can do something with. So since our restriction is that our curve lies on our sphere, we know that we have this relationship, which is that x squared of t plus y squared of t plus z squared of t plus w squared of t equals 1, which will allow us to come up with a relation between w dashed and all of the other three things. And that is, in the end, going to be the restriction that gives us our tangent plane. So take a moment and write out the next line yourself. So I want to take the derivative of this thing with respect to t. And our eventual goal here is to find some kind of restriction on this tangent that means that we are living entirely in the tangent plane. I'm going to give you 15 more seconds. Okay, so hopefully you've got something. Let's see if you got what I got. Probably I'm right. So if we take the derivative of x squared, we get 2x, and from the chain rule, dx dt, plus 2y dy dt, plus 2z dz dt, plus 2w dw dt is equal to, class vote, hands up who thinks the right-hand side is 1. Hands up who thinks the right-hand side is 0. Good, everyone. Good, good. We have compulsory voting in Australia. When we do class votes, everyone commits. I don't care if you're wrong, but you've got to commit. Okay, so we have this, but actually we know quite a lot of stuff. Because at t equals 0, x of naught is equal to 0. And y of naught is equal to 0. And z of naught is equal to 0. And w naught is equal to 1. So this means this term vanishes. This means this term vanishes. This means this term vanishes. And what we are left with is dw dt at t equals 0 is equal to 0. So what we're saying is the tangent space, the restriction we need is that all the vectors have dw dt equals 0. And in fact, if we go back to our two-dimensional tangent space, we can see that's exactly what's happening here. This is horizontal with respect to the vertical coordinate. There's no vertical change. The derivative with respect to w is 0. So this is consistent with what we know from our lower dimensional picture. And what that tells us, if I put this all together, is that gamma dashed of naught, so the derivative of any curve that is part of my tangent space, is x dashed of naught, about which I know nothing, y dashed of naught, about which I know nothing, z dashed of naught, about which I know nothing, w dashed of naught, about which I know something very important, that it's 0. 0. And this describes my tangent plane. Now, because x dashed and y dashed and z dashed can be anything, the tangent plane is the set of vectors A, B, C, naught, where A, B, and C are arbitrary. So these are the set of all possible tangent lines you can have at the peak. And it's exactly what we expected. It's a three-dimensional space glued to the top of our three-sphere. So it's a little bit of a strange idea to start speaking about tangent places in this abstraction, but of course this will let us talk about derivatives in this kind of space, and that's going to be very, very important. In a sense, this is revision from 1962. You know, the concept of a tangent plane is hopefully something that you've seen before. But that's kind of the reason why I ramped it up to 100 straight away. I promise you the things you haven't seen before I will introduce a bit more gently. But here we just wanted to test the edges of what you know about tangent planes to really think about how they'll generalize, because these ideas are going to be important for what we learn down the track. Now, I want to give you a 5-minute break because more or less we're halfway through the notes I plan to get through. So take 5, and then we'll come back fresh.
Definition of tangent spaces in just more generally. From what I understand, right? I'm still waking up. It's not.
That's fine. Me too.
Tangent space. Here we've looked at tangent spaces as specifically the graph of the differential in terms of the graph of the differentiable function. But more generally, for like a manifold, right? And like a manifold.
Yeah.
One can only define, right, tangent spaces on smooth manifolds, right?
Yeah, but we're restricting ourselves to that.
Yeah, of course. I'm just like,
yes.
There's only a notion of the tangent space.
Because that's when you run into issues. Remember I stressed the dimensionality of the tangent space has to be the same. If it's not smooth, you can't even guarantee that.
But can you still even talk about tangent space? Because there's no notion of differentiation on a non-smooth manifold. It's only topological. Right? Like,
I don't want to say no, because almost everything has been generalized in some way.
Yeah.
But certainly not just by tweaking this definition kind of hits the wall at that point.
I'm just like saying there's no notion of really like direction.
No.
On like just at least from my understanding, general topological manifolds.
And, you know, this is an issue, and you run into this when you solve PD. That's basically why we had to invent weak solutions.
I don't know what a weak solution is.
But you will by the end of third year. So there are mathematical ways of dealing with situations where you can't construct a tangent space. But I don't know if there is some like pseudo-tangent space. That's not typically the mechanics
but
we would use.
If you do have a n-dimensional smooth manifold, you can always go and guarantee the tangent space is n dimensions, except if it's maybe a manifold with a boundary. Like at the boundary point, you might have less
That's why we needed the open set.
Pardon?
That's why when we defined a tangent space, we called it the open set around zero.
Yeah,
if you don't have that, it all falls to
and also, you could define the tangent space not only as a set of like lines through it in a given coordinate, in any given coordinate chart, but also like could you also define it as like the set of kind of like all like partial derivatives? I was thinking of like in a given coordinate chart.
Yeah, there would be a way of rewriting the definition in that.
All ways of partially differentiating, like in respect to each direction.
Basically, what you described is two ways of notating the same idea.
Yeah, I'm just I'm just confirming that you can. Like, I'm not missing something.
Yeah, good thinking. Hello. We can always find a to parameterization. Later on in the semester, we will talk about how yes, it does, but that can always be in this new definition we like TPG, it's equal to definition. Vectors are only three conversations here. The idea of a vector having a vector is just an object. In some sense, I believe it's here. So in some sense, a tangent plane, it doesn't like have a position in space, it's just like, yeah, try not to follow that rabbit hole. Yeah, and this idea of that having a base is just a but the tangent plane is just that. The thing that matters about vector space is its spaces don't exist completely are every vector space points to the origin. So if you want to be I need to I've been asking questions this whole time, not one. All right, we're going to have to kick back off. I had a couple of... Finish what you're saying now. Stop. Good. I had a couple of people ask the same question, and it is a relevant one. This doesn't seem to pass through the point we care about. What is going on? Remember, the tangent plane is really about the shape of the curve. Remember, it's the set of all the vectors, but the idea of a vector being embedded at a point is just an artifact that we keep in our heads. Really, this is kind of the correction to 0, 0, 1. So if I move a little bit away from 0, 0, 0, 1, then I'm 0, 0, 0, 1 plus a little bit of my tangent space. So remember, tangent spaces are centered on the origin, but it's the orientation, it's the set of vectors that we can then glue to this point. So there is a little bit of sleight of hand when we talk about tangent spaces versus tangent planes. So maybe I should have said space here, I guess would have been better. No, the tangent plane is the set of all vectors which are the derivative at that point. Don't worry too much, follow the algebra. These are the tangent lines to all gamma of t for which gamma of naught equals 0, 0, 0, 1. So this is talking about their derivative, not their value. So just separate those two things and you're in pretty good shape. The tangent plane is talking about the derivative at a point. It is helpful to imagine it glued to the surface, but actually it's a vector space. And we know vector spaces have a whole lot of important properties, including that they go through the origin when taken on their own. So good questions, all of you. And this is one of those examples where maybe tying too much to the pictures and not the definition can lead you astray if you aren't careful. But that's okay. The tangent place is really the tangent vector is really a calculation tool. It will come up a lot more as we talk about vector fields. Let's do another example just to warm us up after our little break. And then we will learn a bit more theory, which again, probably you've seen before, but maybe not written in the way that I'm going to. So, a very important group in the theory of Lie groups and differential manifolds is the second special linear group, which is a group of matrices. So this is the set of all matrices A, B, C, D, such that A, B, and C, and D are real, and the determinant is 1. The special linear group. It has a lot of important properties. If you do things like differential geometry or Lagrangian and Hamiltonian mechanics, you will meet these sorts of objects. So it's defined by an equation in R4, but like, I drew this picture to help you along. There's no picture I can draw like that here. This is one of those situations where the geometry in which we're working is not something where visualization is going to help us. Happily, that is why mathematicians use definitions. So if we just follow the definition, we'll see where it takes us. Locally, and I'm going to make the assumption that that A is not 0. And in fact, the point that we're going to put the tangent plane at is going to satisfy that, so it'll be a good assumption. So locally, as long as A is not 0, then this is a graph, ABC, and 1 plus BC over A. So D is kind of fixed. So in fact, you can think of this as an interpretation of the graph of this function D as a function of A and B and C. Because when we pick out A and B and C, D is fixed. So we have this graph, and we want to say what is T at a particular point, and I'll put that in a moment, of SL2R. A point. So here I picked 0, 0, 0, 1, a nice sensible point. But that's not really a thing I can do here. What I'm going to do is work out the tangent plane of this set at the identity. So if you're a bit rusty, when I say identity, I can see firstly it's going to be an element of SL2R because it has determinant 1. So the identity is in my set. I can work out the tangent plane at that point. And that is exactly what I will do. So M of t is A of t, B of t, C of t, D of t. And I'm going to let t trace out paths in this group to figure out what's happening and, importantly, what their derivatives are. And I want to pick my parameterization. So I got another neat question, which is, why do we only care about 0? And we can always pick a parameterization where that's true. So we do, because it makes our lives easier when we write down the definition. So we always assume that the tangent plane corresponds to t equals 0 is equal to 1, 0, 0, 1. So straight away, I know that A naught is 1, B naught is 0, C naught is 0, and from those I could have told you that D naught is 1, because this is an element of my set, but we can see it anyway. Okay, so we have our M of t, and it's just a matrix where all of the terms are parameterized by t. Well, to work out M dash of t, its total derivative, maybe what I'm about to do is something you haven't done before, but if you want to take the derivative of a matrix, you can just take the derivative of its entries. So it's A dashed of t, B dashed of t, C dashed of t, and D dashed of t. And we're going to say our curve is completely arbitrary, so we don't know anything other than the fact that it lives in SL2. So I'm going to say whatever its derivatives are, they're alpha, beta, gamma, delta. I don't know what they are. Different curves could have different values. Is there some restriction that will let me restrict the set of these that lie in the tangent plane? And we're actually just going to do exactly what we did before. So for M of t to be an element of SL2, we require A of t times by D of t minus B of t, C of t to equal 1, which is to say my M of t can traverse anywhere it wants as long as its determinant stays fixed at 1. And we take the derivative just like we did before. So